astronauts, they cost $130,000 an hour just to keep them alive. We're talking food, we're talking water, and the mission control to keep them moving throughout their day. We don't want them moving bags around, we want them doing the science. One of the hardest things about in-space robotics is we're in the vacuum of space. You have solar radiation pressure, in shadows it's super cold, in the light there's an insane temperature gradient. So if you have the dexterity and now the latency, all of a sudden you can teleoperate robots for $130,000 a year versus $130,000 an hour of labor in space and actually do meaningful work.
At our core, that's the enabling factor that we're building, and we're building our robots to take care of.
Here on the left is actually our 2D microgravity test table. So essentially what this is it's a large glass platform, and then on top here, this contraption you can see is what we call an air-bearing chassis. We used to use these nitrogen tanks here, which are manufactured for applications like this, but found out that a cheaper way to get more volume and to actually store more nitrogen at a higher pressure was to reuse ones from high-pressure paintball guns. Here what we have is a pneumatic system of different regulators that allows us to push out that high pressure nitrogen through these air bearings. So what you can anticipate is a thin film of gas coming out over here, and then essentially that sits between the chassis and the table, allowing it to slide around. So now if we put a force on it, that robot is going to float across the table, and we can basically fly it around as if it's in 0G.